Okay, class, welcome to lecture 14. So we're back on track with lectures. Got a new setup that I hope the sound will be better. I bought a microphone. Everything seems to be working out, so we'll see. Okay, so this word sampling distribution will come in later, but we got a lot to talk about before we get to that. What we want to do now is I just want to say that what we have been doing so far isn't really stats. What we've seen is basically just background to do stats. And now we've seen enough to really do stats. So, so here's the big picture idea now that we can sort of talk about because of all the stuff we've seen. So the idea is that we're trying to study populations. So given a population, this is a word we haven't really used, but it just means a group of things to study with some sort of number associated to it that you can find the mean of. So it has to have a mean. And I'm going to use this fancy Greek letter mu instead of m. And it has a standard deviation. Sigma, another fancy Greek letter. What we do is we take samples. So this is the first big picture idea. So the population maybe is like the California population, and I want to study, say, the heights of all the Californians. Then the heights, there is some average height of all Californians, and that would be mu here, and there would be some standard deviation of all the heights too. But the point of samples is that populations are typically too big to ask everybody what their height is, so figuring out this actual mean is really hard to do. So instead what we do is take samples, but each sample, so if I get like 20 people in California, each of those samples, each of those smaller groups, well, that has to have a mean too, a mean of their heights. So you might ask, like, okay, well, how is that related to the mean of everybody if that's just a few people? So each sample has a mean which may or may not be close to the population mean, meaning this fancy letter mu. But that's okay because something interesting happens. So that mean that you found from that sample, it might be right on the money, it might be way off, but that doesn't matter because what we can do, we can look at this interesting data set, which is going to consist of all possible sample means. So consisting of all possible sample means. So for every possible sample you could get from the population, each of those has a mean. So this data set has all of those means as its numbers. And then, due to the magic of math, it turns out that the mean of this new data set that you create by getting all possible samples is exactly equal to the population mean. So this very weird math fact. And then this data set is normally distributed, which really means that we can use all the fancy math that we just learned about previously. So this is a bit abstract right now. We'll see lots of examples and it won't be so bad. So all this theory sort of makes it seem like. So on Moodle, I'm going to put up some links to some websites where you can play around with some stuff that I'm going to talk about. So here's one example coming from this website. So consider, let's think of a bag of numbers. So we just have this bag, and the numbers in the bag are from 0 to 20, and they all appear equally often. So if you want to think about it, I guess it's more of a barrel than a bag. You could think about it like there's 100 of each number. There's a bunch of zeros, a bunch of ones, a bunch of twos, and so on. They all appear equally often, but they're all mixed together. So here in this little mini example, the population is all the numbers in the bag. And they have some mean. If I add them all up and divide by the total amount, they have some mean that I could calculate. So I'll do that right now. So since each number has an equal chance of being selected, well, there's 21 numbers, and they each appear equally often. From 0 to 20, there's 21 numbers. It must be that there's a 1 over 21 chance for any number to be selected if you like randomly picked one. So then you could think about this in a distribution sense with that little chart. But you could also think about it using a graph. So you could think about it this way. Each number from 0 to 20, but it's sort of divided into parts, so you can't pick like decimals or anything, just the whole numbers from 0 to 20. They each have the same probability of being picked. Then, so what's the population mean here? Well, it's the mean of all the numbers in the bag. So I can sort of cheat because they're all equally distributed in there. I can just think of it as the 21 numbers I have, and I'm just adding up 0 to 20 and dividing by 21. So if you do that, that'll end up being 10. So the population mean is 10 in this wacky little situation. So then the key is like generally, like in other places, not here, of course, this would be hard to find. I wouldn't know that it's 10. In this situation, just because I created a specific way, I could just calculate the mean. But in other situations, I wouldn't be able to find the mean of the entire population. So instead, what I would do, because I don't know that mean, is I would take a sample. So very fancily, people would call these subsets of the population. So what this means here is I would just take a couple of numbers out of the bag. So maybe I'll take them of size 5, which I'll call little n. So I could randomly open this bag and pick 5 numbers. So let's just pretend I did that. So for example, maybe I found a sample with these 5 numbers by just randomly picking 3, 10, 11, 12, and 16. So this is a sample of size 5 because it has 5 things in it. And then what I could do is I could calculate the mean of this sample that I just found. So then for each sample, get a sample mean, which just means the mean of this sample, which would be 3 plus 10 plus 11 plus 12 plus 16, divide that by, there's 5 of them. So if you do that, that'll turn out to be 10.4. So I made this sample up, but technically speaking, samples need to be random to really mean anything, but we're gonna gloss over that for now. So don't worry too much about that. So technically, I'll write it though. Samples should be found randomly for the math that's secretly in the background to work. So what this really means is that each thing in the population should have an equal chance of being picked. Whereas I just made this one up. I didn't actually pick them randomly. Each thing in the population should have an equal chance of being picked by whatever method you're picking. Being picked, wow, I can't spell today. Picked by the method. Okay, but we're gonna gloss over the randomness for now. So the point is I take a sample, find the sample mean, but then I do this a bunch of times. So then take lots of samples. So on this website, this will do this for you at the click of a button. So each one has its sample mean. So I just did one up there, but it was 10.4. But then, so say I get a bunch more like 10.4, 10.2, 9.9, and so on. I'll just get a whole bunch of them. These are all sample means. So then if you draw the resulting histogram using this data set, so all those sample means you've got, you draw the histogram. What interestingly happens is after you do this, and after you find enough, what you'll see is that the distribution, the histogram, starts to look normal, meaning you get this nice bell-shaped curve for your histogram. Where the x-axis is your possible sample means. But even better, the mean, so that now we have a normal distribution which has a mean and a standard deviation. So the best part is that the mean of this distribution will be the population mean. So for us, that means the example we just did, that will be 10. The center will be 10 in our example, because that was the actual population mean for what we were talking about. And notice this happens even though the original population was not, we're not picking from a normally distributed set of data. So this was not a normal distribution. So even though I pick numbers that don't come from a normal distribution, so here I'm picking 0 to 20, where it's not like they're distributed in a bell curve shape or anything, I still get a normal bell-shaped curve for this creation where you take all the possible sample means and make a histogram out of them. So this will always happen. So this happens no matter the original population. And you can see this on this website, but I'll post two websites where you have various shapes for your population distribution. So that means like the data could look like that or something for your population, or it could look super weird or whatever you want. Doesn't matter. If you do this sample mean process, where you take all the sample means, then those will be on a normal curve no matter what. Okay, so that's the math background, but we'll see that it won't be so bad when we do actual examples. Okay, and then the nice part is that this mean is the same as the mean of the population no matter what. So over here, the mean might be like right there, and here, I don't know, the mean could be there. But no matter what, the mean when you do the sample process will be in the middle of the normal distribution. It'll be the same as the population mean. So what about the standard deviation? Because a normal distribution has to have that too. Oops, what about standard deviation? So remember, that tells you how far it is to the inflection points. Well, it turns out that it will be something easy to calculate too. It will be the standard deviation of the population divided by the square root of the sample sizes that you used. So for us, it would have been 5, because I was doing samples of size 5 up there. Okay. So we're going to introduce lots of fancy notation later, but let's jump into examples. But I guess I should say this just to summarize. So in general, if you have a population with, so in the beginning, we're going to start off knowing the mean, mu, and the standard deviation. But in reality, and later on, we'll see how to do something different. So, but for now, what we're doing is we're given the population mean and the standard deviation. Then we get this distribution which is going to be a normal distribution. And it's the distribution of possible sample means. And it's always going to look like, since it's always going to be normal, it's going to be a bell curve. And the middle of this bell curve is always going to be the mean of the population. And because the standard deviation is the original standard deviation over the square root of n, then that's how far it is to the inflection points. So I just have to add and subtract that amount because that's the standard deviation of this distribution. Okay, so now let's answer questions just to sort of ground ourselves. So with this, we can answer new types of questions that seem very similar to questions we've already answered. So here's an example that will seem familiar. The population mean for IQs, so this is saying that the average IQ of the entire population is 100, and the standard deviation is 15. So what did we do before? So before we would say, what's the probability that if I just like pick some random person that their IQ is say above 110 or something like that. So we're always asking the question about like, what are the chances that one person is somewhere on this distribution, is above this or below this or between these two things. But now a new question is asking something like this. Find the probability that, so instead of just having somebody be above or below something, we're going to look at a sample, that a random sample of some size, 10 in this case, results in, and we're going to ask about the sample mean, results in a sample mean, let's say greater than 110. So it's a bit different than what we asked about before. It's very subtle. So a very subtle difference between this and something like we might have asked before, which was something like we would have said, find the probability that a person, a single person, instead of a sample, just has an IQ. Whoops, I already blocked out too much. Has IQ greater than 110. So in that situation, what we're doing there is we were assuming that IQs were already normally distributed. Oops, middle's 100. And then we would say like, okay, well, I'll look at 110, which is about there, and I'm trying to find this area. So that was the before type of question. But now we're looking for sample means on the sample distribution.